Picture this. You're inside a structure built entirely from frozen water. Outside, the temperature is sitting at 40 below zero. Inside, you're warm enough to sleep without a fire. No insulation panels, no synthetic materials, no modern engineering, just snow, shaped correctly with a tiny hole punched in the roof. And that hole isn't a flaw. That hole is the reason the whole thing works. Most people hear igloo and think primitive. Think again, the igloo is one of the most thermodynamically efficient shelters ever built by human hands. And once you understand the physics layered into every single design choice, from the shape of the dome to the angle of the entrance tunnel, you'll realize the people who invented it weren't just surviving. They were engineering deliberately, systematically, and with a level of accuracy that modern thermal scientists have gone on to confirm in controlled laboratory settings. Let's start with the material itself, because this is where most people's intuition fails them completely. Snow feels cold. Snow looks like the enemy. So why would you build a warm shelter out of it? The answer comes down to what snow actually is at a structural level. Snow isn't solid, it's mostly air. A well-cut snow block is somewhere around 90% trapped air by volume, and air is one of the worst conductors of heat in nature. Thermal conductivity for still trapped air sits at roughly 0.024 watts per meter Kelvin. Solid ice conducts heat about 100 times more efficiently than that, so the ice block freezes your hand, the snow wall does not. Every block in an igloo wall is millions of tiny thermal dead zones stacked together. Heat tries to escape, hits an air pocket and stalls. The air pockets are doing all the work. Now here's the question that throws people off. If snow is such a powerful insulator, why does a snowbank feel cold when you press your hand against it? Conduction. Direct physical contact. Your skin touches the surface and heat transfers immediately across that bridge. But inside a finished igloo, you're not touching the walls. There's an air gap between your body and the snow. That gap eliminates conduction almost entirely. What you're left dealing with are convection and radiation. And this is exactly where igloo geometry becomes something special. Heat rises. That's not a metaphor, it's density physics. Warm air is lighter than cold air. In a rectangular room, warm air hits a flat ceiling, pools in the corners, and radiates straight out through the roof. You're heating the one zone that does you the least good. The igloo dome solves this completely. Warm air rises and spreads evenly across the curved interior surface. There are no corners for cold to anchor, no flat plane for heat to concentrate and escape. And because a dome minimizes surface area for any given interior volume, there is simply less wall for your warmth to bleed through. Run the geometry on a cube with the same floor space as a standard igloo and you get 30% more surface area, 30% more heat loss. The dome isn't a stylistic choice, it's the most thermally efficient enclosure shape that exists. The entrance tunnel is the next piece of the system, and most people overlook it completely. Igloo entrances don't open at floor level. They tunnel downward first, then curve back up into the living space. Cold air is denser than warm air, so it sinks and stays low. It fills that downward tunnel and sits there. It cannot rise into your living area because physics won't let it. Your warm pocket stays sealed at the top where lighter air naturally collects. You can actually measure the difference. The entrance tunnel sits around -20 degrees Fahrenheit. Climb 3 feet higher into the dome and the temperature jumps to 40 degrees. Same structure, same snow, 60 degrees of difference based purely on air density stratification. Now we get to the part that surprises everyone, the hole in the roof. Your instinct says seal the igloo tight, lock in every degree, but a sealed igloo will eventually work against you, and not because of the cold outside. Every breath you exhale pushes moisture into the interior air. In sub-zero conditions, that moisture doesn't disappear. It finds the coldest surface it can reach and freezes onto it. Over hours, frost builds up on the interior wall. Frost is ice. And ice, unlike the snow it replaced, is a thermal conductor. Your insulating wall is slowly converting into a heat sink from the inside out. The vent hole at the peak stops this cycle at the source. Warm, moist air rises to the apex and exits. Drier air circulates in through the entrance tunnel below. The interior stays dry. The snow walls stay porous and insulating. The vent isn't losing you heat, it's protecting the material that's keeping the heat in. There's also a carbon dioxide problem that matters for anyone spending a full night inside. CO2 is heavier than oxygen, it sinks. Without any air exchange, exhaled carbon dioxide gradually builds near floor level, which affects blood chemistry and reduces how efficiently your body regulates its own temperature. The convection loop created by the vent hole manages this passively. You never have to actively think about it. The physics handles it for you automatically. The final layer is one most survival guides never mention: phase change energy. As the interior of a well-built igloo warms slightly from body heat or a small flame, the innermost layer of snow begins to melt just a fraction. Melting absorbs a significant amount of energy locked into the transition from solid to liquid. Then, when heat production drops, that thin melt layer refreezes and releases that stored energy back into the space. The igloo functions as a thermal buffer, absorbing heat spikes and releasing them slowly, stabilizing the interior temperature without you doing a thing. A tent does none of this. The moment your heat source stops, a tent's interior temperature drops immediately. An igloo's interior holds. So what you actually have is 5 interlocking systems working together: a wall material that traps air and blocks conduction, a dome shape that minimizes surface area and heat loss, an entrance tunnel that physically prevents cold air from entering the living zone, a roof vent that manages moisture and drives a passive convection loop, and a phase change thermal buffer built directly into the walls. No moving parts, no manufactured materials, no power source, just geometry and the properties of water. The people who built the first igloos weren't guessing. They were observing, testing, and refining across generations in conditions where a bad shelter meant death by morning. They didn't have the vocabulary of thermodynamics. They had something better. They had results. And the physics they discovered is the same physics engineers study today. Sometimes the oldest solutions are old because they're right.